Hello everyone. Today we are going to discuss the third application of Gauss's theorem. Okay, that is the electric field due to a sphere, a hollow sphere. So look at the heading, that is electric field due to a uniformly charged. So it is uniformly charged, thin, it's very thin, and a spherical shell. So it's a shell. Shell means it is a hollow sphere. So look at the diagram. We have a shell and its center is O, radius of the shell is R, and inside it is hollow, and it is uniformly charged. So this is the charge on its surface. So this charge, let it be its Q. Okay, so you are going to find out the electric field outside the sphere, inside the sphere, and also on the surface of the shell also. So these three we are going to find out today. Let us start with the point outside the shell. Okay, so now the first one is outside, the electric field outside the shell. So this is the shell, and we know the shape of electric field lines that will be directed from the shell towards infinity. So this is the direction of electric field. I am not going to draw each and all, so some of them. So all these are the electric field lines. So I have to find out the electric field outside the shell. So randomly I am considering a point P here. So this is point P. Okay, so I need to find out the electric field at this point P, and we are going to use Gauss's theorem. And we know to use Gauss's theorem, we have to imagine a hypothetical, the closed surface called Gaussian surface. So let us consider a Gaussian surface outside. So it's convenient, it's a spherical Gaussian surface, and this entire spherical Gaussian surface is enclosing the shell, the spherical shell. So this dotted line, so this is the Gaussian surface. Okay, so this, and its radius is R. Its radius is R. So it's clear that the point P is also a part of the Gaussian surface. Point P is also a part of Gaussian surface. So you can say the radius of the Gaussian surface is small letter r, and the radius of the shell is capital R. So see, it's clear that point P is outside the shell. That's why small r is greater than capital R. So look at this. So anywhere you see small r greater than capital R means the point P which is outside the shell, Now look at this. The direction of electric field will be from, okay, so sorry, it is starting from here, so it will be like this. So this is the direction of electric field. Now you are going to find out the value of this E. Okay. Now let's start with the formula of electric flux. What is electric flux? The number of electric field lines passing through an area normally. So we are going to find out the electric flux through the Gaussian surface, the spherical Gaussian surface. We know the formula, it is phi is equal to E dot A, or that is E into A cos theta, EA cos theta. And what is theta here? Theta, clear. Anywhere in the Gaussian surface you consider the areas. Let's consider a small area here. So see the angle between area, vector and electric field, they are parallel. Anywhere, if you consider here, anywhere in the situation, it is clear that the electric field line is normal to the Gaussian surface. Normal means area vector is parallel to the electric field. So parallel means theta is equal to 0 degree, though that is phi is equal to E into A, EA. And now what is this A? This A is the area of the sphere. So don't get confused. What is A? It is the area of the sphere. Area of the sphere, and that is A is equal to, it's a sphere. So what is the area formula? A is equal to 4 pi small r square. 4 pi small r square. So you can write this formula is equal to flux phi is equal to E A. What is the A? It is E into 4 pi r square, equation number 1. Got it? And now, by Gauss's theorem, we know phi is equal to q by epsilon naught, equation number 2. Now look at equation number 1 and 2. Okay, from 1 and 2, you can equate. So from 1 and 2, you can write down E into 4 pi r square, sorry, small r square. 4 pi r square is equal to q by epsilon naught. Q by epsilon naught. Or finally, you can write down E is equal to, it is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught cube divided by r square. Q divided by r square. So anyway, remember what is this value? It is k. So you can also write down that is equal to kq divided by r square. So you can also write down kq divided by r square. Okay. We have one more formula for the electric field outside the shell. Okay, so we are going to derive that new formula. We know surface charge density is sigma. Surface charge density means it's the charge per area, charge per unit area. So that is Q by A. See, it's A means here I'm writing it's A dash, where A dash is the area of the charged body. What is the charged body? It's a shell only. It's a shell. So it is A dash is the area of the shell. Okay, not the Gaussian surface sphere. Gaussian surface is a sphere, so that is also same formula. But remember the radii are the different. Gaussian surface radius is small r and shell is capital R. So now what will be the value of this A dash? That A dash, you know, it is 4 pi capital R square. Now I'm going to make some changes in this formula. So that is Q is equal to, it becomes sigma A dash. Now what is the value of A dash? That is sigma into 4 pi capital R square. Now I'm going to substitute this in our formula. What is the value of E is equal to? It is KQ divided by small r square. Now what is the value of A? Sorry, K. K is, we know it is 1 by 4 pi epsilon naught. And now I'm going to substitute the value of Q over here. So what is the value of Q? It is this. It is this. So I can write that is equal to 1 by 4 pi epsilon naught into, what is the value of Q? It is sigma into 4 pi capital R square divided by, it is small r square. Now look at this, 4 pi can be cancelled, and finally you will get E is equal to sigma capital R square divided by epsilon naught small r square. Epsilon naught small r square. So this also gives us the equation of what? Equation of electric field at a point outside the charged shell. We have to discuss one more thing here, that is, anyway we have derived outside at the point P, which is at a distance r from the center of the shell, and it's E is equal to kq by small r square. Okay, that we have derived. Now let us consider this entire charge of the shell. Now see, the charges are distributed on the shell. This, you can see the circle, the inner circle. That's not a circle, it's a sphere only. So it's a shell only. That charge is Q. Okay, now imagine that complete charge is concentrated. Just imagine it's concentrated at a point O. That's plus Q. Same charge, but we don't have the shell. It is completely, on the center of the shell, and now that point is O. So just imagine. Now point P is the same. So point P is here, which is at a distance R. Now, if the second, we are imagination, it's okay. If you imagine it is So it is like this. We don't have a shell, but the same charge is concentrated at the center of the shell O. Now the direction of electric field, it's positive, it will be in this direction. Now this electric field, due to a point charge at distance P, at distance R is equal to, we have already derived before, KQ by R square. It will be KQ by R square. So look at this board, look at the board. Both equations is equal to KQ by R square, and here also exactly the same equation. Now what is our conclusion? What is our conclusion? We can say that we can imagine only for this case outside, if a point P outside the shell, we can imagine the shell as a point charge, and which is concentrated at the center of the shell. On both the cases, the electric field at the same distance R will be the same. Electric field will be the same. See both the equations. Okay. Next, the second case, the electric field on the surface of the shell, okay. So let us do this one. We have again the same situation. We have a charged shell and its charge is Q, center is O, and R is the radius of the shell. Now the point P where the electric field you have to calculate is on the surface of the shell. So I am marking here is the point P, okay. So this is point P, and the distance is at a distance small r. Now see here, the point is on the surface of the shell, so the distance r and radius of the shell, it's the same, so that's why I written here on the shell r, small r is equal to capital R. Now we know the direction of electric field will be from the shell towards the infinity, okay. Now again we are going to consider, you are going to use Gauss's theorem, so we have to imagine a Gaussian surface. In this case, what should be the shape of the Gaussian surface? Again, it should be the sphere, clear, and it should consider that, you remember in previous case also, the point P which we consider should be a part of this Gaussian surface. Now point P is on the shell itself. So listen carefully. In this case, the shell itself is the Gaussian surface. I repeat, the shell itself is the Gaussian surface. So I am not going to draw anything anyway. Remember, the shell itself is the Gaussian surface. It's a shell at the same time, Gaussian surface also. Okay, so it's very simple. In this case, R is equal to capital R. We have already derived the formula for electric field outside, that is, it is KQ, clear, divided by R square. And also we have derived both the formula, E is equal to sigma capital R square divided by epsilon naught small r square. So no need of derivation, it's simply you can substitute the value of small r. So when you substitute the small r, it's capital R in this case, because see here, the radius of the shell and the radius of the shell and the radius of the Gaussian surface, they are the same. So this equation, now electric field at a point P on the shell, it becomes KQ divided by capital R square. In the same way, the second equation, in the denominator, small r, right now it becomes capital R square, and these two will be cancelled, and then E is equal to sigma by epsilon naught. So these two equations will give you the electric field, the net electric field on the surface of the shell. Now the third case, which is the last one. the electric field inside the shell. So again the same shell, but now you're going to calculate the electric field inside the shell. Okay, let's consider randomly a point here. This is point P, which is at a distance small r. Okay. So in this case, look at this. Small r is smaller than capital R. See? So here capital R is bigger. Now you have to use the Gaussian surface. Gauss's theorem. So let us imagine a Gaussian surface where point P is a part of that Gaussian surface. So again, sphere is the most convenient one. So we are going to use, imagine a spherical Gaussian surface. So, okay, yes, this. Okay, so this is our Gaussian surface. In this Gaussian surface, the flux phi is equal to, you know the formula, that is Q by epsilon naught. And do you know this flux is equal to 0? The flux is 0. What is the reason? What must be the reason? Let us recall Gauss's theorem. The flux is equal to 1 by epsilon naught times the net charge enclosed by the Gaussian surface. I repeat, enclosed by the Gaussian surface. Come to this diagram. Look at this diagram. So this dotted line, this is the Gaussian surface. Now inside the Gaussian surface there is nothing. That means the charged shell is outside the shell, outside the Gaussian surface. Inside the Gaussian surface there is no charge. So the value of Q is equal to 0 here. The value of Q is equal to 0. So it's 0 by epsilon naught. So the flux is equal to 0. So that the flux inside the shell is 0. Or we can say that the electric field inside the shell is equal to 0. So remember, the electric field anywhere inside, it can be here, or anywhere in the shell, inside it will be 0. Now, the last part is the graph. That means E versus distance. Okay, the electric field versus the distance of the point from the shell. So we are starting this distance from the center of the shell. Okay, let's come to this diagram. So if imagine the point P is at the center only, at the center. It is inside the shell, so electric field is 0. So when R is equal to 0, then distance is 0, because at this point R is equal to 0. So when R is equal to 0, electric field is also 0. So in the graph, I am going to mark this point is here. Now I am going to consider another point which is here. This is point P. Now what is the value of R? The value of R is, it's not 0, clear, but that point R is less than the radius of this, because we know the radius is capital R. So the R is less than R, but still electric field is 0. So for example, this is the value of R. So but electric field is 0. So I can mark it over here. Now I keep on increasing the distance. So now the point is here. But still it is inside the shell. Electric field is still 0. And keep on increasing. So electric field will become 0. Why 0? Because all these points which I consider, they all are inside the shell, and we know electric field inside the shell is 0. Okay. Now finally I have reached its surface. Now electric field is not 0, and we know the value of that electric field. So at this point, now this is R is equal to R. So here it was R is less than R. And now the electric field suddenly increases here. Suddenly it increases to a point here. And you know what is this electric field? That we know that is E is equal to KQ divided by capital R. Clear? So this has the maximum electric field. I'm sorry, it is not Q by R, it is Q by R square. Okay, so that was the maximum value. So now see the graph, the shape of the graph, it starts from 0. So till outside, on the surface, so electric field is 0. So whenever R is less than R, electric field is 0. But when R become capital R, the electric field suddenly increases. And what is its value? It's KQ by capital R square. Got it? Okay. Now, let's go outside. I'm going to consider the point outside. So when outside, we know the formula is E is equal to KQ by small r square. Or also we can say that E is proportional to 1 by r square. So see what? When the distance increases, electric field is decreasing, because see, look at this, so they are inversely proportional. Electric field is inversely proportional to the square of the distance. So when I am increasing the point, a distance anywhere outside the shell, the electric field will decrease and it will decrease so. Clear? So what about this region? In this region I can write down it is, it is R is greater than R. So this graph shows the variation of electric field with the distance from the center of the shell. Remember, from here to here electric field is 0. Here it is electric field is 0. Okay, and at this point maximum electric field is KQ by capital R square, and on further you can see the electric field is decreases and its value is equal to KQ by small r square. Okay.